Question number 44, CY 2022, and the question is the number of new SO stretching vibration bands observed in the IR spectrum of the high spin Mn-DMSO whole 6 3+ complex is, where DMSO equals to dimethyl sulfoxide. Option A, only one band. Option B, two bands with intensity ratio 1:2. Option C, 2 with intensity ratio 1:1. And option D, 6 with intensity ratio 1:1:1:1:1:1. Now you have to choose the correct answer among those four options. Coming to the answer, first let me draw the structure of Mn-DMSO whole 6 3+, where Mn in +3 state and it has an octahedral geometry and it will be a high spin complex. This is the square planar part of the octahedral system. And this is the square pyramidal part of the octahedral system. Okay, so this is the Mn-DMSO whole 6 3+ complex. Where Mn in +3 oxygen state, octahedral geometry and high spin complex. Thus, in free metal ligand, where manganese D3+ has 4 d electron, it will be like okay. So these are the orbital of manganese 3+, 4 electrons. Now, in octahedral geometry, they will split these 5 equal energy d orbitals, which will split into different sets of orbital. This is T2G set of orbital and EG set of orbital. This is in octahedral crystal field. Now, the T2G set of orbital will form by the combination of the XY, the XZ and the YZ orbital, while the EG set of orbital will form by the combination of the x square minus y square and the z square orbital. Now we have to put this 4 electron accordingly. Hund's rule and Aufbau principle. That is from lower energy to high energy, and first every orbital has to be filled by 1 electron, then the other electron of different spin will be filled in each orbital. Now every orbital has an electron of same spin. Now you can see that T2G set is partially filled but equally, but this is not in the case of EG set of orbital, which is partially and unequally filled. Equal, partial, filling of electrons, but in this case unequal partial filling of electron. Because of this unequal and partial filling of electron in EG set, these two different sets of d orbital in octahedral crystal field will be further splitted, and that will be the lowest orbitals are dx set and dy set. This is dxy. This is how the T2G set will split. Here in the EG set, the lowest orbital is dz square and the topmost orbital is dx square minus y square. This is how the EG set will split. This is the energy order. Okay. Now put again the electrons following Aubert principle and Hund's rule. You will see that the dz square orbital have one electron, but the dx square y square orbital have no electron. Okay, the dz square orbital have one electron and dx square minus y square has no electron. And what will form through this electron configuration, this unequal partial filling of electronic configuration? What will happen? We will see next. So coming to the orbital geometry, you can draw the orbital as, okay, this is x-axis, this is y-axis, this is z-axis. The dz square orbital is like this. Okay. So the dz square orbital is aligned along the z-axis. Okay. Now the dx square minus y square orbital. Okay. This is x, this is y. Okay. So this is the geometrical spatial distribution of d x square minus y square orbital. Aligned along x and y axis. That is along xy plane. So you can easily see both these orbitals, that is dz square and dx square minus y square orbital, are aligned along the axis. Now what are the remaining orbital dxy, dyz and dxz? They actually are aligned in between the orbital. For simplicity or for example, I will show one of the orbital again. This is x, this is y, z, this is y. Okay. Now the dxy orbital will be this is dxy orbital. Okay. Align in between x and y axis. It is also aligned in xy plane but not along the axis. Xz and yz also you can draw similarly like that. There is xz orbital will be aligned in between x and z axis in xz plane, and yz dyz orbital will be aligned in between y and z axis in yz plane. Now coming to the general structure of any octahedral complex. This is structure of octahedral complex. Okay, these are ligands. You can see the ligands are coming actually along the x-axis. If you think this and this x-axis, this is y-axis, and this is z-axis. So the ligands will have an interaction with the metal d orbital which are aligned along the axis. So only two orbitals are aligned along the axis. One is dz square and other is dx square minus y square orbital. So they will have some kind of interaction with the metal d electron present in these two orbitals. If there is an electron in these two orbitals, thus the ligands will have some repulsive interaction. And if that repulsive interaction is not same, what I trying to say that if there is an electron in imbalance of filling of electron in these two orbitals, that is dz square and dx square minus y square orbital, so the ligands coming along the axis will have different kind of different measure of repulsive interaction with the d electrons present in these two orbitals. Now thinking of this system of Mn DMSO whole 6 3 plus, where the d orbitals split it like this. Okay, easily you can see that there is an electron in z square and no electron in dx square minus y square orbital. Thus, the ligand will face much higher repulsive interaction when they are coming through z axis, since there is an electron in the dj square orbital, than the ligands coming along x and y axis. Now, going to the original structure of the compound, if the MnDMSO whole 6 C plus is an ideal octahedral system, the structure will be okay. This is ideal octahedral geometry, but because of this Z elongation effect. What is Z elongation? That is the ligands coming along Z axis, it has a more repulsive interaction than the ligands coming along X and Y axis. And because of this repulsive interaction disbalance, the metal ligand bond length along Z axis will be higher than the metal ligand bond length in X and Y axis. So because of this Z elongation, the structure will look like easily we can see the metal oxygen bond length along z-axis is higher along xy plane. Okay, now this elongated bond length along z-axis will have an effect on the SO system. So there are two different SO systems now in the molecule xy plane, one along z-axis and one along xy plane. The number of DMSO ligand is 2 along z-axis and number of DMSO ligand is 4 along z-axis. Okay, and since I already told that this extended metal ligand bond will have interaction with the ligand that is actually on the SO bond, since there is two different ligand along y-axis and along x and y-axis. Thus, because of the SO stretching frequency in the IS spectrum, two bands will appear. With intensity ratio 2 along z-axis and 4 along xy plane, there is intensity ratio 2:4, this 1:2. So this will be your answer, which is option B. 2 SO stretching frequency bands with intensity ratio 1:2. You will find the reference through lecture on Jahn-Teller distortion by Professor Debashish Ray, Department of Chemistry, IIT Kharagpur. Thank you very much.